Okay, folks, I'm going to try to make a sequence of videos. This is for section 4.6, which is on the topic of linear approximations and differentials. So I'll make a sequence of videos on these, and I'll post them to D2L as quickly as I can. Unfortunately, we've got another snow day, so I guess so it goes. All right. We're going to return to a problem that we talked about at the very beginning of this course, and that is how can we use lines, specifically tangent lines, to approximate curves. And what we're going to do now is we're going to reframe the idea of a tangent line, and in this section we're going to call it a linear approximation or a linearization. Okay. So as a reminder, this is our equation of the tangent line here that we've been using. And if I solve this for y, then I can express it this way. So what's going to be different now is we're going to think about y as a function of x. Okay. So what we're going to do in this section is we're going to take complicated curves, like maybe this blue curve right here, okay, that are difficult to evaluate. Maybe it's a square root curve or a cube root curve. It's hard to plug values into it and get and crunch the numbers and get an output. So instead of doing that, what we're going to do is we're going to input x values into the tangent line approximation of that curve at a particular point. So that's a little bit heady. Let's just give this a shot here. We're always going to pick an anchor point A, and at that anchor point A, we're going to build the tangent line. Okay, so we're going to build this function LA of x, which is equal to, and it's just the equation of the tangent line, f prime of a times x minus a plus f of a. Okay. So as a reminder, this is just your tangent line here, and now I'm just giving it a new name, LA of x, to linearization. So the idea about a is that it's supposed to be a point that we've easily measured in the function. So this is the ordered pair a comma f of a. And we know about the behavior of the function at that point. We know what its functional value is, y, but we also know that the slope of the tangent line at that point is f prime of a. So once we've got the linearization, once we've built an equation of the tangent line, we can use it to approximate other points on the function. So let's suppose I want to know the value of this point right here. So maybe this is some value x. Well, I would like to know then, my goal in these sections is to figure out, well, what is f of x? Okay, so we're going to assume that this function here in blue is too complicated to easily evaluate. So instead of plugging x into the function and trying to evaluate it, we're going to plug x into the linearization at that point. And notice, let me put a different color there. So we're going to plug the function, the value x, into the linearization, and we're going to get a y value like this. So this is going to be LA of x. And I know that this drawing is a little bit cramped. The idea is that the green expression here, the green point on the curve, has a y value, a height, that's very close to the orange area on the blue curve. So rather than plugging things into a function, we can plug them into the tangent line anchored at a point and get a pretty good approximation for what that will be. So continuing with the notes, provided that we've got a function that is differentiable, now that's key, we're going to build an equation of the tangent line at a point A, and for that to work we need f to be differentiable at A. Then we'll say the linear approximation of f, or the linearization of f at the point A, is given by this expression here. So LA of x, and it's just what we've been writing. It's just the equation of the tangent line. F prime of a times x minus a plus f of a. At this point, I think it's a good exercise to identify what is the variable in this long expression that I've got on the right. So here's the expression on the right, and I'm asking you, what is the variable in this function? Okay. Notice that in this problem, we're assuming that a is fixed, and it is x that is our variable. So this is our variable x here that will be changing as we work through this. Okay. The idea is that once we've built this linear approximation centered at a, we can use LA of x to approximate values of f of x for values of x that are near x equals a, and that's sort of a rough, we're not really going to define what we mean by near, but if you go back to this picture right here, notice that if I pick points, x values that are further and further away and try to use the red line to approximate the blue curve, that approximation is worse and worse. And in fact, to get a better approximation, I want to move closer and closer to the point on the curve where I made the linear, where I built the tangent line. Okay. So let's go ahead and look at an example. So in example 5 here, I want to find the linearization of the function f of x equals the square root of x, and I'm going to anchor it at a equals 4. And I'm going to use that to build a linear approximation so that I can guess, or I can make an approximation for what the square root of 3.98 is and what the square root of 4.05 is. So pause the video and think about this for just a second. So I think that all of us could make a guess as to what these values should be. We know that the square root of 4 is 2, and so we believe that the square root of 4.05, for instance, should be something close to 2. In fact, we know it should be something a little bit more than 2. But the question is how much more than 2? Okay, and that's what we're going to determine with our linear approximation. So just to give you a visual for what we're doing here, I've got here in blue, I've got my square root curve. And we're assuming that it's difficult to plug things into this square root curve. It might be we don't have a calculator. It might be that it's computationally intensive for a computer to do it because we have to do millions of these calculations. Or it could be that maybe we've never experienced this square root curve before, and so the best we can do is use a line to approximate it. So our goal is to find out output values for this blue curve f of x, but rather than plugging points into the blue curve, we're going to plug them into the yellow tangent line because lines are much easier to work with than curves. So here's how this process works. We need to choose a function. Well, in this case, f of x was given for us, so there wasn't a lot of choice there for the function. Our function is going to be f of x equals the square root of x, and then we need to choose an anchor point. So let me get caught up here. So we're going to choose f of x, okay. And the choice for f of x should mirror the operation that we're trying to do. That's why I suggested we use square root of x, because we're trying to determine the square root of 4.05. The next thing we need to do is choose an anchor point. So in this section I use the anchor point to refer to the a value, which is where we can easily work with this function. So notice that I do know what f of 4 is. I know that this is the ordered pair. When x is 4, we get the output 2. So this will be my anchor point right here. And so who is a? In this case, a is going to equal 4. It is the point where we are, math people use the phrase, we are centering the linearization around the value where a is equal to 4. Okay, now that we've done that, let's build the linearization. So we're going to say that the linearization of this function centered at 4 in terms of x as a function of x will be f prime of 4 times x minus 4 plus f of 4. Okay? So folks, don't let your eyes glaze over. I know that we haven't used this notation before to describe a linearization. What is this over here? It is just the equation of the tangent line, right? So this is just the y equals and then the expression for the tangent line. So don't be intimidated by this expression. Okay, so in order to use this function, now it's very clear. Where is the variable? Variable x is just this. So we're going to plug into this function. We're going to plug in both 4.05 and 3.98. Okay, so in order to use this, we need to determine what f prime of 4 is and what f of 4 is. Well, we said f of x is the square root of x, so f of a will be f of 4. And the point here is 4, which is the square root of 4, which is equal to 2. Okay. Then we also need to determine f prime of a. So let's first find f prime of x. F prime of x, that's the derivative of the square root function. So that means that f prime of a, which is equal to f prime of 4, is just 1 over 2 times the square root of 4, which is equal to 1 over 2 times 2, which is equal to 1/4. Okay? All that said, we can now actually give the linearization function. So our linearization function is L4, so the linearization centered at 4 is equal to f prime of 4, which we said was 1/4, times x minus 4, that was our anchor point A, plus f of 4, which we said was 2. So we're going to use this function right here to approximate the square root curve. So the point is, folks, this is a little bit hard to get your first time through. On the right-hand side, I have a linear function. This is a line. Lines are far easier to work with than most functions. Okay? So it's a lot easier to plug in values of x into this line right here than it would to actually plug in values of x into a square root function as far as doing the computations goes. Okay? Remember, this is an application to the derivative, or in the application section. So let's go ahead and find L4 of 3.98. Okay? So again, we're trying to get a guess as to what the square root of 3.98 is. A good approximation is what the square root of 3.98 is. Well, we all feel like, well, it's that 3.98 is a little bit less than 4, and so the square root of 3.98 should be something a little bit less than 4. But the question is, or excuse me, should be something a little bit less than the square root of 4, which is 2. But how much less than 2 is the question? Okay. Well, let's find out. So we plug in 3.98 in for x into our linearization function, and we simplify. Folks, I'm going to do this without a calculator, so I'm going to work with fractions here. So we get 1/4 times negative 0.02 plus 2, but that's 1/4 times, so the fraction negative 2/100 is negative 2 over 100 plus 2, which simplifies to be 1/4. Excuse me, I can clean that up now. So let's make that negative 2 over 400 plus 2, which is equal to negative 1 over 200 plus 2. Now all I just need to do is get a common denominator here, and I get negative 1 over 200 plus 400 over 200, and I get 399 over 200. And 399 over 200 is 1.995. So this is not the square root of 3.98. What we're claiming is the square root of 3.98 is approximately the linearization of the function evaluated at 3.98, which is 1.995. And of course, if you check with the calculator for the square root of 3.98, you get something very close to this. So that's our answer. So we knew, I know this doesn't seem like an amazing result, we knew that the answer was going to be something less than 2. The question was how much less than 2, and it turns out to be about 5/1000ths less than 2. Okay. So let's also now do the linearization for 4.05, which was the second point we were asked to look at. Okay. So we did 3.98 and 4.05. So if we plug this in, we get 1/4 times 4.05 minus 4 plus 2, which is equal to 1/4 times 0.05 plus 2. Let's see here, that's 5/100ths, so we get 1/4 times 5/100ths plus 2, or 5 over 400 plus 2. Well, if I'm going to add 2 to 5 over 400, let's write it as 800 over 400, and I get 805 over 400, which can be reduced down to, it reduces down to 2.0125. So again, what we're doing here is we're approximating the square root of 4.05. I am never plugging 4.05 into a square root function. Instead, I'm plugging it into a linear function. I'm plugging it into a line, and I'm saying that the square root of 4.05 is approximately 2.0125. Well, that's pretty good, because if I write out the square root of 2.05, the square root of 4.05, let's go to 4 decimal places here. we'll go to 5 decimal places. I get 2.01246, which is indeed, so this is truly what the, well, up to 5 decimal places, what the square root of 4.05 is. It is very, very close to our approximation. Okay? So I'm going to do this. I don't know how well this is going to work on the video here, but I'm going to zoom in on this picture here. And the idea is, and I'm going to exaggerate this slightly, we wanted to figure out what the square root of 4.05 is. Well, let's pretend 4.05 is right about there. And you can't really tell this, but rather than plugging it onto the blue curve, rather than finding out what the square root of 4.05 is, I went ahead and went along this gold or yellow curve and plugged it into that point there. But of course, they're so close to each other. In this case, oops, let's zoom out here. In this case, these two values, if I plugged it into the yellow curve, this is what I got. And if I plugged it into the blue curve, I got something close to this. These two values are accurate to at least the thousandths place, right, which is a pretty good approximation. That's the idea of linearization. I'm going to pause the video now and do some more. I'm going to jump into differentials, and then I might come back and do some more linearization examples.